Good morning, and thank you for joining today's webinar from Spec Innovations, Predict, Analyze, Optimize, System Simulation with Innoslate's MBSE tools. My name is Taylor Duffy, and I will be the moderator for today's webinar. First, I would like to go over some housekeeping. During the presentation, feel free to send us questions, and we will get them answered in the Q&A part of the webinar. You can also interact with us on LinkedIn through the Innoslate users group or through X using the handle @SpecInnovations. The webinar is being recorded and will be made available to you after the live presentation, so keep an eye out for it in your inbox. Now, I would like to introduce you to our presenter, Spec Innovations President and Founder, Dr. Stephen Dam. Dr. Dam has been involved with research, experiments, operations analysis, software development, systems engineering, and training for more than 40 years. He has also received an Expert Systems Engineering Professional (ESEP) certification from Incosi. He is currently applying systems engineering techniques to various DoD, DOE, and commercial projects. Feel free to send him any questions through the LinkedIn users group or send him an email to steven.dam@specinnovations.com. Now, I'll hand over the controls to Dr. Dam, and we'll get started.
Thanks, Taylor. So today we're going to talk about how to set up the simulations in Innoslate to do model-based systems engineering analysis. And particularly, we're going to spend some time on the Monte Carlo and why that's helpful to you. The discrete event are the two major ones we provide. And also looking at how this is important to your overall lifecycle engineering process. Why do we simulate? Why do we model? All that kind of thing we'll talk about. And then how do we communicate the results? Because it doesn't help to do the modeling if you can't communicate the information. So, and of course, we're going to spend most of the time in the tool itself. Setting up and running Innoslate is pretty simple. We support a variety of different languages in Innoslate, including SysML, UML, LML, and IDEF. Particularly, though, for simulation, we simulate the behavioral model, which is in LML, it's called an action diagram. In SysML, it's called the activity diagram. Now, the reason we do that is that most of the things we're interested in systems engineering are processes. And it's the process elements of what we're trying to understand most completely. Mechanical engineers worry more about the physical architecture of the system, and so the electrical engineers about the electrical elements, and many other engineering disciplines. But in systems engineering, our biggest concern is how do we make all this work together? And the way we do that is through our processes. And so modeling the processes through the behavior diagram, again, the action diagram or the activity diagram, depending what language you're looking at. And we don't care which one, you can toggle between the two as you need to. There's a little simulate button in that diagram. It's a drop down and lets you select either the discrete event or the Monte Carlo. I like to call the discrete event simulator our debugging tool for the Monte Carlo, because it turns out Monte Carlo is really important, as we're going to talk about in a minute. I should also mention that we do have a state machine diagram. It can be executed using computable attributes, which we have now in Innoslate. So we have the ability to define equations, not only as a parametric diagram, but also in LaTeX, and then use the LaTeX information to create execution. And so you can bring those two together, and we've been able to do that now. I'm not going to talk about that today in any depth, but if that's something of interest in the future, we're happy to go through that in more detail. So key parameters, I'm not sure what happened to all my pictures. Oh, I know why. I've probably been logged out. So I am in Innoslate. Yeah, it signed me out. Interesting. So thought it was still live, but it wasn't. Okay, so we do have two-step authentication. There we go. Sorry about that. So let me go back to where we were. And we had the picture there, so I guess that's what threw me off. I thought we were still logged in. Okay, so now Hopefully you can see now the picture. Okay, so looking at the Monte Carlo and how we analyze system performance. Again, one of the things is we don't know numbers exactly. Okay, in fact, very often you'll find the key parameters. At best, you may know the range of those values. And so, and the other factor is there's a lot of randomness in almost every process. You think about the processes you deal with, uh, everything has failure modes. What's the probability of a failure mode? Those kinds of things you can model and add into your models to make them more rich and more complete. And so those are things we want to try to do as we're doing our modeling, right? Well, the key is then if I know that I can't specify something exactly, and I don't know the exact distribution. What I find myself very often, particularly very early in the life cycle, I'm doing this kind of modeling simulation early, I find myself using a triangular distribution because I can use my engineering judgment to make what's the best case, what's the worst case, what's it most likely to be as a rough idea. And then as time goes on and you make measurements, you get results from design engineering processes and what they do and their development work, you should take those results and then bring them back into Innoslate. We can curate anything from other design engineering tools as artifacts. But what we want to do is extract the data that's important, the essential elements of information that are important that we want to bring into our model, and then use those distributions to what we call verify the simulation works correctly, or calibrate the simulation. That's another term we use sometimes for that. So that's the idea here. So that's why Monte Carlo becomes very important. And you don't realize how important a Monte Carlo simulation is for this in this domain until you have one. We were working on a project a number of years back with a different tool, which had a very nice discrete event simulator, but didn't have the way to do Monte Carlo. And we were able to kind of rig it to do Monte Carlo analysis for us, but it took us 2 days to get the results, to actually go through the analysis and pull out the data elements from the multiple runs of the discrete event simulator that we were able to do. So one of the things when we designed Innoslate, we said we can't have that. That's just too painful. And so we made sure we had a very robust Monte Carlo simulation capability. It does look at the cost, schedule, and performance factors, particularly resources and asset utilization. So we usually model the people part of it, the teams, as assets, and then other resources we could do like fuel or other things that you're trying to make sure that you have for resources are in the resource radar. So that's how those are done. I'll talk a little bit more about the panels later here. So another thing is in a lot of people say, well, gee, this stuff looks awfully simplistic. Can you really model something really detailed with behavior? Well, we've been able to model very detailed things. So in very complex behaviors. And so particularly looking at the discrete event simulator, you can go in and use that information to help you build the models, build the things. And particularly one of the things we provide in each action diagram is this idea of decision points. And a decision point is a special type of action or activity, if you prefer that term. And what that does is it allows us to just to make these logical determinations. But the nice part is then that's allocatable to who or what does them. Okay, so that gives you some real benefits in your modeling. In it, we have the ability with any action to have a script associated with it, and we use JavaScript. Again, the browser is written in JavaScript. The simulators are written in JavaScript, so it makes sense to use JavaScript. I know a lot of people want to use Python. I understand that, but JavaScript is just as easy, really is almost as easy as Python, I should say, to code in. And so if you do Python, you probably can do this too. And the benefit of it is we actually, for almost all the, most of the decision points, we provide you built-in scripts. So the basic things you would do all the time, like a loop iteration, is something that we built in for you. So you don't have to worry about it. And in fact, I think this is an example, this is an example of probability branch. So this is showing us the script. So we actually create that script for you, and I'll show you how we do that in the demonstration portion. But this is basically saying if 95% of the time it's going to go the normal path, and the remaining set of the time it's going to go down the contingency path. And so that's a thing you'd expect from a probability script. Let's see what else I want to say about that. Yeah, again, one of the nice things about the action diagram, that better than in a sense than the activity diagram, is we explicitly model the resources. So now you can really create that more complex model without a lot of scripting and much more effectively. So that's another thing that we've tried to do. So again, we understand that a lot of systems engineers are not coders and don't want to be coders. We get that. That's fine. That's why we give you very low code to no code kind of activities here. And I'll talk a little bit later about where we can get to things that are really complex kind of modeling with it. So part of this is, why do we do this? Why are we doing this simulation in the first place? So simulation provides a means to verify the logic of your models. If you are not simulating your models, you do not know that they work. Okay, it's like writing code and then even compiling it and then not executing it and saying, okay, that's perfect, this must be ready to go. And anybody who's written code knows that's not the way that works. Usually the first few times you execute something, it doesn't do what you want it to do. I rarely, over the years, as long as I've been coding, that I've been able to write a code and have it execute right away perfectly. Okay, that's just a very rare event. So you have to expect that. Okay, so the key is that if I can do this and I can verify my logic, that's great. But I want to do more than that. I want to be able to understand, how is the system going to perform, particularly as I'm early in the life cycle and I'm looking across the V there, and I'm realizing that I'm going to deploy something into an operational space. I want to be able to predict how it might perform in that operational space. And I'm going to make all kinds of estimates early in the life cycle to guess what that might be. But there's also become the constraints for your problem as well. Once you come up with the right set of things in the beginning, that'll help you, give you the behavior you want at the end, then you can use those parameters as your main metrics to help focus your development work. Make sure you can meet those needs, those things. You can accomplish those as you do more detailed design engineering work. Again, once the detailed tests and analyses are performed at the design engineering level, you again capture those results as artifacts, as I mentioned earlier. You can take the results in our documents view or compilation view. There's a couple ways to use that. And then the distributions of the models can be updated to better match that reality. So again, our motto is simulate early and often, okay? And very early in the life cycle. So you should be, if you think about the V diagram, right? You think about the V, right? You're starting at the architecture level. And by architecture, we mean the enterprise architecture, the big picture, how things are working across the whole system of systems. And I want to see how the system I'm going to develop is going to behave in the operational space. So I'm thinking about not only test and evaluation at the end, operational test and evaluation, when I'm doing that early architecture work, I'm thinking about operations to support as well, and disposal. So I have to think through that whole life cycle, and to do that and to be able to kind of predict that, I want to be able to use simulation, and discrete event Monte Carlo simulation helps me do that. Okay, so communication. So a lot of things you're trying to do is get the data out. And we provide a number of different ways of doing that, depending on the simulator, particularly. There's all kinds of ways to view time. What are my time results? Because timeliness is one of the key parameters we're always looking for, right? It's quality, quantity, and timeliness are three of the key things you're always looking to. And simulation can give you at least the quantity and timeliness. The quality part is a little harder, although things like reliability and those kinds of things can be modeled as well. So ultimately, yes, you can do all three of those key parameters we're looking for. So time, again, very important. Cost, of course, is another major factor, right? Cost, schedule, performance. We're trying to optimize those three factors and mitigate risk across our development process. So again, these are critical items that we're trying to do. Resources, resource allocation, resource usage. Everything depends on what are your resources. How much fuel do I need to operate, for what distances, in what situations? What are those factors? I mean, you can think about those, and we have all kinds of ways to view those in terms of radar charts over time, things like that. You can also do all kinds of export of data using the scripting, where you can actually write things to the console, or maybe even write files. I've got to think about that one, but I think you can. Anyway, so all kinds of reports are output from the simulation. We have, of course, the pictures of any diagrams, things like that. There's CSVs of the diagrams as well. So you can actually have all the data points that are in there captured as a CSV, put it into Excel, do whatever kind of diagramming you want to do and analysis you need to do there too. For our Gantt chart, we have the ability, which is on the Discrete Event Simulator. We have a Microsoft Office, Microsoft Project XML export, but also on the Monte Carlo, we provide you a range of those, both the high and low for cost and time. So again, that you'll see those different projects. If you're using it for project planning purposes, you can do that. And of course, the entire simulation be captured as an artifact. And that's what the picture here is showing. This is an artifact of a simulation run. And it is an option in the simulator. And I'll show you where it is there. And once you do that, then now you can curate that and you can capture that over time. It keeps all the reports associated with that you created. And so if you need that data at any point in time, you can always download it and get that information as well. Or just view the simulation and download those files as you need them. Okay. So good. So finally get past the slides, get to the tool. Okay. So in here, let's make sure this one's operational. So I'm going to go take one of our models and sorry. There we go. So this is our FireSat model. Many of you are probably familiar with the FireSat problem over the years. That's been a staple of many of the space books, at least the SMADs, and some of those other textbooks that talk through this model. Anyway, so we've modified this model a little bit. We actually get into the force fighting itself, the firefighting itself. So for those who aren't familiar, the rounded rectangles are actions, okay, and they can be loaded serially in the process, or there are constructs which are special decision. We call them decision points. So you have the or, the sync, the loop. Now people say, well, gee, don't you need more of that? By the way, the parallel is a sync point. Without the sync point. So it's basically it's a simplification. So since a lot of people see things that they want both paths to execute before they move forward, then they don't need a sync point if that's the case. The sync point's there for things like timeouts and things like that. You might think of it as like a non-exclusive or. It's another way to think about the sync point. So in here, we have the different elements of information. So again, so those points are your decision points. And you can see here an example in OR. So I have two paths, normal and contingency. So it's one or the other. This is an exclusive OR. I could put XOR on it, but we just said it's an OR. And then once those complete, you can then move on. So this is the way you read this. Now, there are these parallelograms, which are input-output elements. And IOs give you the ability to track your input-output information. They can be even used in the simulation as a variable. You can store values in it. Here's also where I can use distributions to show the size of things. So again, I can do that as I need to with it. The last item here is the hexagram. It's purple, but you can see it's a hexagram. And you see that it is a resource. And attributes are here, initial amount, minimum amount, maximum amount. So resources can be produced, consumed, or seized. In other words, things like if you wanted to model memory usage. So your memory as a resource, I have, 15 gigabytes. Okay, now I have, how much do I have memory usage that I'm going to use of that? What's available, how many applications can I run, things like that. I'm going to pull from the memory, but as soon as the application completes, I'm going to give back the memory, right? So again, that's the seize part. Also notice we do dotted lines, dashed lines to indicate differences. Now, another thing that sometimes throws people off a little bit is the fact that we have this gray parallelogram. And that's an IO also, but it means it is optional for execution. That's all the optional means. It doesn't mean that this information isn't needed here or might not be used here. It just means it's not going to affect my simulation. I'll show what that means more down here. So here's an example. So in here, does a fire exist? So there's some logic in there to make that determination. And it's a probability branch, is the way we've set it up for right now. So then it makes the determination yes. So then it identifies that there's a fire. There's some decomposition going on there. But then it executes this. So this next one here can't execute until it receives this IO, which acts as a trigger. And when you're doing this, you're bringing something into an object. You have the ability to make it a trigger or optional. So if I make it optional, it'll turn it gray. I don't want that. I want it to be a trigger. Okay, because that way there's no reason to do this if there's no fire, right? I detect the infrared emission. So again, this is a way you can take things that are happening in parallel actors, okay, because that's what this is, parallel actors occurring. And then these are the actions that are being performed by those actors. And if you look at this now, again, we use in LML, we call it an asset class. So that's the assets. Those are what we call branch assets. So that explains this one here, the branch asset, and what that's for. So you can see how that works with it. So again, what this did was when I put this action on this line with this asset, I can see it create a relationship for me. Let me just go to the active relationships. So it's performed by payload. So hopefully you can see that. So that's an automatic allocation that occurs. So as you're drawing, you are capturing data in the database. You're creating relationships between things, okay, between the different data elements. And so you're doing a lot more than just drawing. You're really understanding what's going on in terms of the data and the information that you're capturing as you go through the whole process. Well, decomposed lets you we go down another level. Here we're seeing our forest fire come into play, and this is the loop where you're fighting the fire. So let's look down one more level here. And now the way they approach firefighting is kind of interesting. They try to take teams from different directions and corral the fire, and so they can ultimately close it off. That's what they try to do. Oftentimes the fires get so big, it's very difficult to do that. They put blocks and things like that to keep it from happening. But anyway, so that's one of the mechanisms that goes on. So what we did in this model is we're showing the firefighting teams, and they're fighting the fire. The fire is coming in here, and they're using water to fight the fire as the resource. Now, we do have a little bit of information here saying, well, what happens when the water runs low? I'm going to have to refill the water tanks, of course, right? So let me go look at that. That's a script, and it's our resource script. So again, you have ors, probability, or resources, or just a pure script. Okay, so let's just look at this right now. So what does it say? So I selected the resource, which is the water. I then can show some logic of what I want here for that. So if it gets less than or equal this number here, and this is 4,000 units. I don't know what it's gallons or what that units are, but again, you'd associate that with the resource, what that units are, and then the no branch would be the else. Okay, so that's that simple. Now, so when you do that, it creates a script for you. Okay, so this is your user interface for that. Now, if you want to go and see what it did, you just then come here, once you submitted it, come back and select script. And so now the script shows up here. So this shows me what's going on. At the end of the action, it's going to make this calculation. So it's looking at the amount, okay, which is a global ID. It's capturing it. The amount is less than, so this is the amount is of that resource. So this is the global ID for the resource. And then I put in here a print statement, and I forgot the semicolon, but I can't edit it here. So if I want to edit the script, I have to do that from edit. So it's smart enough to recognize that print statement doesn't need a one, but that's better showing of it. Anyway, so you can see here the script and the resources. So yeah, I have to go back now to fix this one. So anyway, so you see that script, and so now I can go use that to help me do the printing. Again, no refill needed. So you're going to see these print statements in the actual simulation run I'm going to do in the console. So these print to the console. Okay, so you can do that. Let's see. So hopefully you see how that works. So again, this lets me model something. Again, we're starting to get complex here. We've got a situation where the water runs low, and I need to do something. I'm going to refill the water, and then the water. This action increases the water, and that's done here. Go to active again, and produces water, and the amount of water is here. So it says 6,000. So 6,000 units there. So 4,000 is kind of, maybe I might want to do that. Maybe I want to be lower than that, but again, this is just a simulation, so we're playing with it. I don't want to change the parameters now, because who knows what'll work, right? Anyway, so let's save that. Go up and back up, back all the way at the top. So okay, so now we're at the top. Now I forgot to show you something earlier. So again, you may prefer SysML, and that's perfectly fine. We do have all the SysML diagrams. All you have to do if you want to see the SysML version of this is just go here, an activity diagram. And so you see the activity diagram. Hopefully this is looking pretty good to you. That's what you're looking for. I can move my ports around a little here, make it a little prettier. I can do stuff like that. But again, these are auto-generated from the other diagram. I don't have to do much of anything here, except maybe move things around and make it look a little prettier. That's about all I have to do. And again, you can move things around pretty nicely here. The simulators are same ones here, Discrete Event Monte Carlo. So you have the same things here. Now it is going to use the resources. It's going to use all the same information we had, the distributions we put in here for duration, all those kinds of things. So these forks are showing decomposition. So it's going to show you all the same information. Okay. I'm just seeing it in a different form. Okay. So I know a lot of people go, oh boy, why that's so hard, this difference. No, it's all the same information. You're just seeing it in a different form. Okay. So let's now simulate. Let's run the discrete event simulator. Now here, again, I have a number of widgets we show for visualization purposes. They're all available down here. So you go select from the set. I think I've got them all pinned up here, it looks like, pretty much. And then similarly for time and resources. Okay. And then here is other things. So this is where you get your 3D action trace. So this is your 3D diagram of the action. I will tell you, if your models are too complex, this becomes, you run out of memory to render this. So we make that's an actual optional item on the 3D trace. Similarly for the Gantt chart, it can burn up a lot of memory. So again, unfortunately, most of the browsers are limited to 2 gigabytes. So at some point you run out of that physical limitation. It's not a limitation of the tool, it's the limitation of the browser. There's also a classic mode that's a little less intensive in terms of the memory usage, but it doesn't have as pretty graphics. So there's your trade-off there. There is help. Access to the help is right here. And then settings. Settings are really important because now there's how we can set settings. Now some of you might like the dark mode. I think that's really hard to show on a webinar like this. That's why you do light. There's a calendar mode. So if you are using this to model a business process or something like that you're looking at, that the calendar time is important, then use the calendar mode. This is not that kind of model, so I'm not going to use that. You set your speed. You go down to real time or slower than real time. Very helpful in terms of understanding and how quickly you want to see things. There's you prompt on no script or automate with no script. Okay, so you can prompt if there's no script, and that would automatically prompt the user for the input. So particularly like an OR, which path you're going to take, and you'd select between the paths that are available. So we've used this for tabletop exercises. So again, we designed it for that purpose, so you can use it for that. So you could execute it in real time and use your people who are interacting with the simulation as your input thing. So that's kind of cool. And then the normal start or debug. So debug starts you in the step mode. So in other words, step one at a time. And then if you are using the calendar mode, we recommend putting in your hours, maybe 1860 hours per year. And then again, that helps you with that. The random seed here is something, if you run the Monte Carlo and there's an error in some random event, that seed will automatically be populated there. And you can then capture that seed and keep debugging with it as you need that. I mentioned earlier that I see this discrete event simulator is my debugger for my Monte Carlo, because that's the Monte Carlo results are what I'm usually really looking for at the end of what I'm trying to do. So again, that'll be there available for you. Make sure once you've made any changes, hit save settings. So that'll be there for you next time. If you don't, it won't be. That includes all these panels you set up and things like that as well. Okay, so let's execute this. And you see it accumulating the hours and cost already. And I'm looking at cost over time, that's accumulating. I'm stepping through, you see it stepping through here. It takes each one of these steps and is going those over a certain amount of time. And again, I'm 10,000 times real time. So you see we're already in the days. So it's going to take a little while. Let's scroll down a little bit more. The Gantt chart's already in spinning mode because it's trying to update fast. There's a lot of data going there. We don't have anything here with resources over time yet. Okay, so there we go. So that we finally got the forest fire coming in. We're starting to see a forest fire hit and build up. And then as it builds to that peak, and now it's being detected by the satellites, the satellite system. In this case, we're assuming one geostationary satellite is this particular scenario. And let me speed up a little bit. And so now, yeah, now the water comes in, the firefighting team starts working. That's the asset utilization. You can start seeing their pattern. The water usage here for it. As you can see, at some point, if you have to have a delay, then you're going to start seeing the fire build back up. And so that's that delay of I ran out of water. And so now I've got to go and provide that to everybody. So again, the fire builds back up a little bit, and then I've got to put more water, and then this is a cycle. So again, that's how we designed this particular simulation. So now it's complete. Actually, that was a pretty fast one. You can see here pretty detailed. The yellow indicates delays that have occurred between actions. So again, you see the information here pretty well on this model. Again, resources here. Here's your resource radar. Here's my cost over time. So, and then here's my, remember that console? These are those print statements I put to the console. By the way, if you put print statements to the console here, that's fine. You may not want to use the console for the Monte Carlo, because depending on how many times you run it, you're going to get that same number of print statements or more each time. It will slow down the simulation a lot when you do Monte Carlo, which we're going to do in a minute. Okay, so that's one run, and of course you could recycle it and restart it and try it a few times more. If you want to export the results, this is how you export it to become an artifact. So this will take everything from the simulation and create an artifact for you, and you'll have that available. Okay, so that's very quickly the discrete event simulator. Okay, so now let's get into Monte Carlo. I want to leave plenty of time for questions. So that's why if I'm rushing a little bit, that's what it looks like. Again, similar situation here in terms of the different information sets, ways to view the information available here. Again, back to classic mode. Here's that console I mentioned. Again, don't use that if you're using print statements a lot, because it will definitely slow you down. And all the other things here. So again, similarly, so let's just kick it off. I've set this to 100 iterations. You can put whatever number you want in there. Obviously, for most complex simulations like this, you'd run it 10,000 times or so, but many more times. But this gives you an idea, at least to start with, a quick look. So again, if we summarize the information here in the status panel, that we were watching the increment of the iterations of it. It shows me a mean and standard deviation of duration and the cost. Okay, so that summarizes all the information there. Then here I have panels showing me time, how much time it's spending in each of the different simulations. Again, this is a mean and standard deviation of these values, all the way down the little ones. So again, disposal takes a bit of time. Kind of interesting in these runs. You see now, probably the most useful to me is this time chart. So I can get the time chart here, and I can see the range. So this is, in a sense, a measure of your risk. Okay, if I'm trying to come up with how long it's going to take to set one of these fires, and how do I budget for that, I'm going to say, well, okay, I'm going to estimate that it's going to be at least a month, maybe, might be in this particular instance. But I see it, I could have a contingency where it might go to 2 months. So you can see that your range in cost is similar, I think. I forgot to mention on the other one, but again, all your reports are right here, the little report button available. And here's where you get to your project reports here on this one. On the discrete event simulator, it's on the Gantt chart itself. I could show that back if that's of interest to anybody. Again, summarizing the resource radar and the asset utilization. We only have one team here. Probably should have set it up with the 4 different teams, and so that way we could see the radar of that, and probably we'll do that in the future for this demo. Okay, so that's the main things with the simulators. So let's see, was there anything else I wanted to show you or tell you about right now? So I think that's most of it. So let's I think it's probably, Taylor, time for questions.
Thanks, Dr. Dan. If you
Yeah.
haven't done so, please send your questions through the panel on the right that pops up after clicking Q&A on the top bar. If you're interested in having our team help you simulate your system using Innoslate, contact our sales team. You can reach our team by email at sales@innoslate.com or through our website, specinnovations.com/contact-us. All right, we've received several questions already. We will answer as many questions as we can before our time is up. First question is, where can we find more information on the way to script the simulations?
So best thing is go to our website. We have a very in-depth website here. So specinnovations.com, resources page. So go to resources. There's a help center with that as well. We have webinars. There's a digital curation station, and we even have some government reference architecture. So lots of resources of information here. Now, particularly if you're thinking about simulation, go to the help center. And then here we have, you can just ask for here, simulation, and maybe I'm interested in advanced simulation. So that's one way to get to it. Another way to get to it is simulation are part of our tools. So I can select tools and I can scroll down to find the simulators. And this will take me to the set of simulations, including that advanced simulation feature that was here. There's also a scripting guide. So these are all things that can help you do things in terms of understanding that each simulator well. I particularly want to talk about the scripting guide. This gives you, for those who are trying to do really comprehensive and complex simulations, this will really be a big help, because this starts you off with the JavaScript basics. So for those who are not familiar with JavaScript, again, at least gives you some basic ideas about it. If you are not into coding, get somebody to help you. In fact, I would guess you could probably get an AI to help you with this these days. Anyway, so again, we have pre-built scripts, and we talk about the pre-built scripts here in more detail, what's in each one of them. What else is here? Loop, resources, iterations. And then then we have examples of things that you might do. So very often you have like two actors, and they're both going, and there's one makes a decision, and the other needs to make a decision, but it has to be based on the decision the first one made. Okay, so this particular asset is going to act. If it says yes, it's going to act on this yes decision, asset one, and the other one is to act on yes decision, asset two. So again, you want these two to be the same. Okay, so again, and then if it's going down no path, you want these two to be the same. If you did this randomly, then that would not work. And that particularly becomes important if you're using IOs to trigger things. So in other words, if I want both of them to come off with a result that I want to read from this branch, then I want to see that from them. And so again, there's things like that you model and get into even more depth. So again, we give you code snippets with these things, and then you can see results as well. So even more advanced things in the simulator, we actually give you the APIs for the sim script elements. This is very in-depth. Again, if you're not a coder, it's not the way to go. It's also incurring costs. Now, in general, incurring costs is very simple. We have a very simple way to do it. It's basically using a relationship, incurs cost, and then we can generate the information for you. But again, this is something you'll dive into as you want to. All the way down. So all the way down, if you keep going down, I'm gonna go fast here. Again, we get into using the Inno APIs as well, not only the SIM. There's two different API sets, SIM and Inno. And so you get the Inno objects here. Again, a lot more depth into the database, gathering information. What else? So I wanted to show you at the very end here. So at the very end, we talk about using IOs. So this is, I mentioned briefly that you can use IOs as values, like a variable in your simulation. We have global variables that you can use as well, but this is kind of a way, if you're trying to really model down at the software level, then this will help you do that, and you can make sure you're representing the software effectively and completely. So you can see you can get down to a pretty detailed level if you want to. I tend to tell people on systems engineering, our job is to specify the requirements for the software, not to design the software. However, a lot of people want to design software through pictures. It's been a goal that I can remember since the 80s. People have had. So this is a way to do that. But in general, I try to tell people, don't do that. You may use it for documentation purposes. Maybe you're trying to document the way code works because you want to abstract it and understand it better. That's a good reason to go down at that level. But otherwise, do the functional requirements and then let the coders write the code. They're better at it than we are as systems engineers. By the way, if you want to get the actual, there's a project that has all these things in it. You can find that. Let's see, we go back up. Let's go back one. So you can find that at our, digital curation station. If you're not familiar with the digital curation station, you want to be, because this has all kinds of examples. There are templates that are available. We have many of the major standards and instructions like the DODI for this. But here's where you see the advanced script example. So click on that, and when you select that, it's a .no file. It has the entire project with all that information in it. So it's all available to you as you need to help you through it. Okay, so a lot of resources are available for this.
Thanks, Steve. Next question, can you import JavaScript packages to the simulation?
I don't know. I'm going to guess yes, because we can take external feeds from sources. So that's possible, I think, but I don't know for sure. That's a great question to ask support, and they will pass that on to the development team.
Next question, any compatibility or cross-functionality with Cameo models?
So no, we're a cloud native tool, and that's a desktop tool. So again, unless we build some kind of special bridge like we did with MATLAB or STK, we couldn't really do that. What we found is that we usually take the Cameo models and export them, or frankly, very often we redraw them because people are unfortunately treating Cameo like a drawing tool. And so they do things like, I remember we were working on one project where they had all their failure modes in a little box in the corner. And that's not the way the world works. It isn't just something, something happens and it goes do that thing in the box. That's not the way the world works at all. It's not the way you're going to model that kind of process. So we actually had to remodel a lot of stuff that we get from Cameo. We have actually a guide for that too, by the way. So if you go to all resources and scroll down just a little bit, there is a guide, CATIA to Innoslate transition. So if you do need to migrate data between the tools, this is a way to do that. We talked about that, similar to the doors in Innoslate transition, but for the specific one that was mentioned, it's CATIA.
Next question, is the IO associated with the parallelograms?
Yes, yes, that is exactly what it is. So if I go back to that model, the parallelogram is the I/O input output element.
Great. Next question. What's the most complex simulation that you've created with Innoslate?
Oh my gosh. So we did a project for the Navy where we were working on a high energy laser test bed when we were down at the software message level. So we took it all the way from and this test bed is trailers of equipment. And we were modeling from, so we actually tried that extremely high level and went all the way down to the software message level. So yeah, it was pretty detailed. That's the last one I did. It's been used. Some of my colleagues used it for modeling a plutonium production plant for Los Alamos National Laboratory. Again, very complex, coming down to how many glove boxes they needed and things like that. So again, particularly trying to understand the sizing of it, the resources needed, and particularly they were trying to do it strategically over a 10-year period. So again, very complex, a lot of detailed things in it, models like that. So we also did one for our lunar rover project where we included MATLAB and STK modeling. So using that, so there's some examples there. Those are the ones I personally know. I know there are other people using it. They're even doing crazier things than that. So, other questions?
What are some of the limitations to the simulations?
So, one of the main ones is memory. Okay, in this, because again, we're running in the browser itself, so that becomes can be constraining. So very oftentimes, a lot of that graphical information we don't calculate, we don't show because it's too much. Couple ways you could deal with that is you can simulate at any level. So I can go down to this level if this is complete enough and simulate it here. So I can do things, and so oftentimes what you do, and again we did this on this high energy laser project because the simulation got to be so big at one point. You can run this, create a distribution in the Monte Carlo, then use that as the action itself. So I could substitute, if I go back, I could substitute this entire action with a distribution that was derived from the Monte Carlo analysis. So it wouldn't be necessarily a triangular distribution here. I'd put in one of the others. And so you can go in to any object and all you do is for size, in this case, but duration, hit the equal sign and pops up this list of distributions. So you select what distribution you want in it. Okay. And so it's a pretty good set of distributions. If you do not see one here, of course, you can script it as in the scripting language itself. So that's the other way to handle that. Any other questions?
That looks like all the questions we have for today. If you could go back to the slides, please.
Yes.
Thanks, Steve. We would like to thank you again for joining us today. As a reminder, we will be following up with you very soon to send you a link to the recording and the presentation slide deck. We hope you can join us for next month's webinar, Navigating Aerospace and Defense Compliance with Model-Based Systems Engineering with Dr. Dam on Tuesday, July 22nd. Your link to sign up will be in the email that is coming soon to your mailbox with the slides and recording. We also encourage you to visit our website and our blog, as well as connect with us on social media. That concludes today's presentation. Have a wonderful day, and we hope to see you at our next webinar.